welcome back. So, today's lecture will conclude module 4 and this is the last two lectures we have seen the introduction to X-ray fluorescence meter and also the X-ray photoelectron spectroscopy and the Auger electron spectroscopy. So, continuing from the last lecture we will see now the instrument, how the XPS instrument works and also some further examples or further application. Okay. So, as you know, the entire instrument, that is XPS and AES, is housed in a single chamber. Now, I will again repeat. So, as you might be aware, in the last lecture what I said was that XPS is dependent on the photon energy, while AES is a secondary phenomena, it will not depend on the photon energy. So, they have provision within the instrument, that is why they have kept both the modes together. So, what it is? It houses an X-ray gun, an electron gun and an electron energy analyzer. So, these are the three important parts. The X-ray gun, as you know, it is a source of the energy, photon energy. Electron gun, sometimes you know, if you are within the scanning electron microscope, then electron gun is required, and electron energy analyzer. So, this is essentially the heart of the instrument, where you actually you try to find out the different distribution of the kinetic energy of the electrons. Okay. So, the electron beam for generation of the Auger electron spectroscopy is conveniently concentrated and scanned across the surface of the specimen for AES analysis. Okay. So, all this is fine, but you require a ultra high vacuum. This is the prime requirement, a high vacuum. The vacuum requirement is higher than SEM or TEM, although I have not covered, but why it is so? Because you know that the electrons, especially the low energy electrons, okay, the low kinetic energy electrons, they will be easily colliding with the gas particles. Okay. So, information will be lost and you will have more noise. So, that is what you require, an ultra high vacuum system. So, as I told you, it will have three parts: X-ray gun, electron gun, ion gun. Okay. But the heart of the process is the electron energy analyzer. So, this is the actual schematic flow diagram. So, you can get the original one from this particular book. So, what you have is, here you have the sample, you see this is a sample. Okay. So, sometimes this sample is the analysis chamber and the analysis chamber is under ultra vacuum. Okay. Along with, so you see the dotted lines, okay, the entire dotted lines is, if we call this is the total system. So, the entire thing is to be an ultra high vacuum. So, sometimes you require primarily three things: X-ray gun, photon energy, the electron gun and the ion gun. The ion gun sometimes you use for certain purpose to make the the surface to be free from the oxides of carbon or nitrogen, because carbon and nitrogen, oxygen, these three elements, it is available in our atmosphere. So, wherever you see in air also you will have these three elements, the carbon, nitrogen, oxygen. Sometimes what they do, along with water vapor, they will adsorb onto the surface. If they are doing so, so what you do, you sometimes clean this surface, or you are doing with some non-conducting material. To make it conducting, you use this ion gun, or you can also use the ion gun to see the depth profiling. What do you mean by depth profiling? It means the sample has this particular depth, you keep on ripping off the electrons from layer by layer and then you see what are the different binding energies. So, from there also you can find out what sort of elements are across the layer of the specimen. So, what they do once the photoelectron is extracted here, whether it is Auger or XPS. So, this is the electrostatic transfer lens. It focuses the electron beam. It will focus the electron beam slowly, and then while it enters here, what happens? This is called the heart of the process, spectrophotometer control unit. This is called the HSA, or the hemispherical sector analyzer, or HSA. Okay, HSA. Now, it has two concentric beams, the concentric spheres. I will tell this later with two different radius, R1, R2. Okay. Now, electrons enter here. Why these voltages are given, I will tell you when I will discuss this particular region separately. Then the electron beam enters here, it goes here, comes back here. Now, this is something called a multiplier, it amplifies the signal, then rate. So, what it does is it counts the number of photons which are coming out from the system. So, it will record a histogram of the distribution of photons with the energies. Then finally, you have a recorder. So, this recorder is something like what you have in the X-ray photometer. So, initially it will be pretty high, then some beam, then it goes down like that. Okay. So, this will be counts and this will be the binding energy. So, when I write binding energy to this direction, it means kinetic energy varies to this direction. I will explain this hemispherical sector analysis later on, but the entire thing, the dotted portion is housed in ultra vacuum. So, what is the range of ultra vacuum you require? It is this much. See, it is a very pretty high ultra vacuum, 10 to the power of minus 8 to 10 to the power of minus 10 millibar. Okay. Why so? Because it will reduce the risk of scattering of electrons with low energy. The low energies, those from Auger, they may easily collide with gas molecules on their route towards detector, so rendering the surface devoid of contamination from the gas molecules. So, Auger electrons and photoelectrons of low energy are readily scattered by gas molecules. So, these two are the reasons, okay, why you use a ultra high vacuum. So, obviously scattering decreases the intensity of the signal and surges of noise. Issue is within a short time span, let us say of 1 second only, they will absorb a monolayer of gas molecules. And the entire recording of XPS spectra takes in the order of seconds. So, even if it is have access of 1 second, it can easily absorb a monolayer of gas molecule. So, what the system is made up of? It is built with stainless steel and crushed copper gasket. Okay. So, gaskets are for joints, overall structure is of stainless steel. The turbomolecular and the sputter ion pumps are ubiquitously utilized in lieu of the diffusion pumps. This because diffusion pumps, you may sometimes 1 or 2 oil molecule may enter inside the system, which will again create problem. There will be scattering. So, to avoid that, you use this turbomolecular and sputter ion pumps. So, this results in lesser chances of chamber contamination due to oil gas molecule leakage. Vacuum pumping itself, so even if you do a vacuum pumping, it is not ensure ultra vacuum, because molecules of the gas while you do vacuum may come through the internal walls of the chamber due to its low pressure. So, there may be molecules which may come through the internal wall even if you try to achieve ultra high vacuum. So, these molecules stay inside. So, what you do is you bake the vacuum chamber, you bake it at a high temperature of 250 350. So, if you bake it, so most of the molecules which are at this temperature range, they will just evaporate out. Baking lets the molecules of gases that are adsorbed on the walls of the chamber to pump out. So, pump out the molecules. Now, another part which actually affects the electron flow is the magnetic shielding, which is due to the Earth's magnetic field. So, a magnetic shielding is therefore used so as to avoid the Earth's magnetic field, because this Earth's magnetic field have a remarkable effect. If not given, it may have a remarkable effect on the trajectory of the signal electrons. So, now let us see what are the source guns for X-ray gun. X-ray photons through electrons with high energy. So, it is similar to X-ray diffraction. So, when high voltage is incident on the metal anode, so an X-ray is generated, and this X-ray, the anode material may be aluminum or magnesium for XPS. So, this X-ray generation uses X-ray lines for the excitation of atoms of the surface under consideration. It can have both monochromatic and non-chromatic sources of X-ray. The non-chromatic X-ray source output contains a continuous distribution with high intensity of K alpha characteristic line. It means that if this is the count of the X-ray photons, the photons will keep on increasing. So, this is the characteristic X-ray of, we call this aluminum K alpha line. So, Al K alpha line. After that, there are continuous, this is non-chromatic lines. So, non-chromatic lines are also there, okay. So, but this one is at 1.5 kilo electron volt, okay. So, the characteristic X-ray is of 1.5 kilo electron volt, but you have a continuous wavelengths which are occurring here with the corresponding photon energies. So, that is what it says, it can be both monochromatic and non-chromatic. The energy of the characteristic X-ray in XPS is lesser than energy of that in XRD. There is a reason for that. For example, the K alpha line for aluminum corresponds to this much kilo electron volt, for magnesium it this much. While the corresponding X-ray lines in case of XRD, you must be aware, those who have read X-ray diffraction. So, they use a copper or a molybdenum, because this will give a resolution close to a nanometer order. That is why they use copper K alpha, molybdenum K alpha. But the issue, we are not using these two elements because their energies are pretty high, 8 and 17. Because issue is, we do not want a such high band this energy, because we need to have a narrow line width. It refers to the energy window. The monochromatic lines should be sharp enough. So, it should have a narrow line width. So, XPS, based on definition, the XPS demands energy lower than 1 electron volt for decent energy resolution. The aluminum K alpha line and magnesium K alpha line shows line width less than 1 electron volt and possess energy pretty high, sufficient for the excitation of photoelectrons. A gun structure, obviously when you have a gun, this can easily switch off between magnesium or aluminum. Usually a monochromatic source is used for high resolution energy. So, how do you remove the other continuous wavelengths? You just put a filter. So, you will have only a single monochromatic X-ray photon entering the system. What are the electron gun? The field emission guns and the lanthanum hexaboride guns are the most widely used in electron spectrophotometer. FEGs are being used very commonly in the modern instruments, because FEG, if you are aware, this is the routine practice where you use this in TEM and SEM. So, that is why these FEGs are commonly used. The lanthanum hexaboride gun is a beam of electron with high brightness and spatial resolution of 200 nanometer after having been concentrated by an electromagnetic lens. So, either guns are used for generating the electrons. Then ion gun, why is ion gun used? I just now explained earlier, let me repeat. Ion flux of high energy is used to clean surface of samples prior to examining. Signal electrons will erupt from the layers of atoms on the surface of the specimen. So, water vapor, oxides, hydrocarbons are removed from the surface. It also sputters out atoms of the sample by layer, revealing that elemental depth profiles. An iron beam via gaseous discharge or electron impact. So, it gives the iron beam via gaseous discharge electron beam, energy window is this much and diameter to be a micrometer. It can scan areas up to 10 to 10 millimeter. Okay. So, as I told you, because of the ubiquitous elements carbon, oxygen, nitrogen in the atmosphere, the oxides of these can be adsorbed onto the surface. So, in order to clean them, to make it contamination free, you use this ion gun. Now, this is the heart of the process, the electron energy analyzer. Now, what it is? Here the if you just recollect our earlier, the electrons are ripped off from the surface and it enters this slit plate with a width W2 and the exits from a slit plate with width W1. So, now what you do is, so an electron voltage is applied. So, this two regions is of R1, this is R0, this is R2. Now, this R1, so this R1 is actually the electron will enter here, it will enter here, exit here. So, what it does is, you have negative potential being applied here and here. So, it means for an electron of energy E naught at S, so there is an electron of E naught at S. Okay, I made it incorrectly. It's actually this, the electrons are entering through this direction and it exiting through this direction. Okay. So, now when an electron enters through this slit window W1 and exits through slit window W2, where we have negative voltage applied here minus V1 and the exterior you apply minus V2, then the total resolution of this XPS is governed by this relation 0.63 W1 R naught. What is R naught? R naught is the particular radius where the voltage is V naught, where the voltage is given as from this expression E naught, the one which is coming through R naught is equal to E into V naught. So, this is the CHA pass energy. So, what is this CHA pass energy? This entire system is known as a concentric hemispherical analyzer, also called as hemispherical sector analyzer. Okay. Now, these electrons are inserted, as I just now told you, tangentially, followed by the channel, finally into the detector. So, the expression for the resolution of this XPS is given by this W1 by R naught. So, you see it is controlled by R naught, and R naught depends upon E naught. So, it means that you can have this particular voltage through this E naught value. So, this E naught energies of electron with this E naught will actually pass through this and come out. Okay. So, let us see in detail how this actually works in different modes. So, this analyzer, for example, how do you define first the resolution? An analyzer of width 1 mm and radius 1.2 meter would be necessary for resolving an electron of 1000 electron volt to plus minus 0.5 electron volt. So, you resolve a electron with this much energy to a resolution of plus minus 0.5 electron volt. The energies of the incoming electrons can be conveniently retarded, allowing the electrons with the attenuated and constant energies to traverse the analyzer. The lens system retarding the energy of the electron also concentrates the electron's energy from the specimen to surge up the throughput. So, it means if I want to suppose there is a sample here, another sample. So, this is the suppose R1 and this is R2, and let us say this is your R0, okay, R0. So, when the electrons enter here and exit here, so suppose this is a slit here. So, now what you want to do is you want to control the various electrons which are coming out from the sample and entering into this analyzer. So, those electrons are characterized by the net energy. So, how do you characterize by the net energy? So, obviously, you slow it down in such a manner such that energies with corresponding to E naught will only pass through this width. So, if that is so, if you see, if you allow the electrons with different energies to pass through, let us say for 10 electron volt, 20 electron volt, 40 electron volt and 80 electron volt. So, as you increase the net energy through which this passes through R naught and exits out, you will get higher and higher intense peak. For example, in this case it is a spectra of polyethylene terephthalate PET with different pass energies. So, for 10 electron pass electron, this we are seeing for the 1s orbital of carbon, you have the intensity to be around 50, while 20 it increases to 120, while 40 it goes to 40 into 10 to the power of 3, it is higher, this is 10 to the power of 2, this is again 10 to the power of 2, this is 3, and 80 is the highest. So, it means the way you allow the particular electrons of definite energy to pass through will actually show up in the output. So, in the output you will get higher and higher intensity peak as and as you allow R naught to grow or you allow the E naught to be higher and higher. So, we should define what is pass energy. Now, the electrons first are concentrated with an electrostatic transfer lens before entering the analyzer in order to reduce the energies up to a particular level, because if they are coming and just hitting the analyzer at a very fast speed, they will be at a pretty high energy. So, it needs to be reduced. So, this is called electron retardation. So, you reduce the speed of these electrons. While you reduce the speed, there are two ways of reducing the speed. One is a constant analyzer energy mode CAE mode and a constant retardation ratio mode, that is CRR mode. Now, CAE mode is used for XPS and CRR mode is used for Auger spectroscopy. Now, what is CAE mode? CAE mode ensures the constancy of the pass energy. So, it means whatever electrons will enter the system, the analyzer will have similar energies when they get out. So, it means they will be, we are looking up at electrons which have similar energies. So, we are going to pass those electrons through that system having a unique energy. and then these energies of the electrons are studied by recording alteration in the retardation of the electron. So, it means while the electrons enter, so if I want to draw here the same thing, so you may understand. So, this is suppose R1 and this is R2. It means if the electrons enter here, it is going out R naught. So, let us say the pass energy is E naught. It means when they are entering, they will having some speed, and but if they are having a certain speed, their pass energy will remain constant, it will be E naught. So, obviously, if you want to maintain the pass energy, you have to retard the electron. So, what it does is with different pass energies, it studies the retardation of the electrons. So, with different energies, you study the retardation, how the electron is retarded, and the way they are retarded, you plot them. So, that will give the XPS spectra. And for the Auger spectroscopy, which is done in constant retardation mode, what you do is you retard all the electrons equally, then you compute the pass energy, just the opposite, converse manner. Okay. So, why we need to do that is because of this resolution. So, expressed in absolute energy, resolution is very important, you should understand. The resolution of 0.5 electron volt is necessary for the entire spectrum. With this resolution is dependent on the geometric arrangement, which includes the hemisphere radii and the slit opening. As I already told you, it will depend upon W1, and we had that factor 0.63 in the earlier slide. This also depends upon this R1 and R2. So, it means it depends upon the geometric arrangement. For example, if for a particular energy of E equal to 200 eV, a CHA needs a 0.025 relative resolution in order to meet the criteria for XPS resolution. So, in the XPS, you need a resolution of 0.5. For a resolution of 0.5 in the actual spectra, you need a relative resolution of 0.025. This is in the instrument itself, in the system itself. But for a higher energy, this much of relative resolution is required, 0.003, one order of magnitude lesser, making it unfurlable. So, the electron energy, the pass energy is made in such a manner, it is retarded such that a low CHA. So, entire thing 10 to 100 electron volt is obtained, so as to retain a constant resolution in the whole range of the spectrum. So, the retardation of 1000 electron volt photoelectron yields the pass energy of 50 electron volt. So, in XPS the spectra are obtained, obviously the retarding electric potential in CAE mode. Okay. So, when you do operate in constant Auger electron mode, what you do is, sorry, the CAE is constant, we did it earlier, constant analyzer energy, In this, you allow the electrons with a constant energy to pass through and then observe the retardation. Now, in the Auger mode, the suppressing the electron signal at the spectrum low energy end is required. So, the CRR mode is equivalent to Auger analysis, as the concentric hemispherical analyzer manifests a low pass energy and transmission rate, because the low Auger electron energy is obtained due to the application of constant retardation ratio. So, what you do is, in this case, if I want to draw it here, while the electrons here entered, they are applied a constant retardation ratio. So, all the electrons are retarded equally. So, if they are retarded equally, so you then find out what will the pass energy. Suppose you put one particular ratio, then you find out the pass energy E naught. Similarly, another ratio, you find out the pass energy, like that. So, you keep this as CRR as constant, you go ahead and define different pass energy. So, for at 100 electron volt and a retardation ratio of 10, the pass energy is simply 10 electron volt. And if you apply this much for an energy of 1000 electron volt, a value of 100 electron volt is required. So, CHA electron transmission is lower at a 10 electron pass energy as compared to 100. So, if you have a 10 electron volt pass energy, so it means the amount of electrons coming through this will be low as compared to 100 electron volt. So, obviously, in Auger the spectra is obtained by altering the CHA pass energy in the CRR mode. Peak identification can be confusing between Auger and XPS. So, various X-ray sources are used to differentiate the photoelectron and Auger peaks. Auger electron kinetic energy, which alters the energy from the primary X-rays. demonstrates a shift in apparent binding by change in the source of X-ray. The Auger peak shifts by 233 electron volt in the XPS spectrum because magnesium K alpha is having this much as compared to aluminum. Then the position of the peaks is very important. It will depend on the spectrophotometer condition on the surface of the specimen. And the XPS peak identification, it requires calibration for specimens with poor electrical conductivity. There is some internal standard. For example, elemental silicon or the carbon 1s peak at 285 electron volt through the organic debris such as carbon, hydrogen in air can be observed on all environment exposed specimens. Okay. So, as I told you, carbon, nitrogen, oxygen are absorbed everywhere. So, you can see these debris Cc and Ch, you can see they will mostly be available in all XPS spectra. Now, if a particular sample of these elements are irradiated by X-rays of K alpha line of aluminum, so the total binding energies will be something like this. So, you see these are different KLL lines, these are LMM lines and these are MM lines. So, if you see the energies of 1s orbital increases, okay, it will increases here, goes up potassium. So, these are KLL lines, similarly these are LMM lines likewise. So, it is given, it continues in the next table also. So, these are again KLL lines, then LMM lines. So, as you go higher and higher, you will get the energies to be higher, and which is the most for the 1s orbital, then decreases with 2s, 2p, and then 2p, 3s likewise. Okay. So, this is an, for example, where can we use this XPS spectra? So, this is an XPS scan where we report the binding energy from 0 to 1200 for a polymer sample. The polymer sample we can tell, you know, the different attachments of carbon. We are expected to get this type of, if it is a fully polymeric sample, there will be only one carbon, you know, you will have various in the monomer, you will have different carbon C1s, you will have C1s corresponding to CH, then you will have here CH, then from here CH, likewise. Then CO also you will have one from here, then one another from here, like that. So, you see you will have the different, you can tell whether the polymer, what sort of attachment the polymer has, and if that attachment is fair enough. So, fair enough means if the polymer is the binding energies you can compare compared to the individual CO, which I have just now I have already placed this data in the earlier lecture. You will compare the C1s orbital energies and the O1s orbital energy to find out whether the polymer is really formed or not. So, if I want to distinguish the entire region, so this is how it looks like. So, see, there is one carbon atom which is sitting here, it comes out here. Then you have both this to be equivalent, A, CH and CH, they are all equivalent, A. Then again C comes, this is C. So, this C1s orbital. Then again another, I am only plotting the 1s orbital of carbon atom, and then you have CH and CH, which is B. So, what are the different types of atoms you can see? First is CO, then you have CH, then you have CH2 based on the. So, this A and B are in this way, it is saturated, unsaturated. So, you see they are located in different direction. Okay. So, those which are at A, they are CH, which is less, and which are done by CH to the end hydrogen atom, they are having higher energies. Now, you can also use XPS for predicting the binding energies. So, more the oxidation state, which is already we have seen in the previous class. So, the binding state of silicon, here also the pure titania without any oxidation states will have a binding energy of 453.9 electron volt. Then you, as you go with higher oxidation state, this increases. So, you have a binding energy shift from 453 to 458. So, 4 electron volt binding energy shift. Sometimes you can also find out whether we have a layer, what is the titania oxide layer, because titania is known to depict 2p doublet, the doublet 2p is occurring at these values for pure titania. So, if you have a pure titania below this layer and this pure titanium oxide layer is around 10 nanometer. So, we will get some additional peaks. So, this particular titania will be corresponding to the one, if I go to the previous slide, to this value. Okay. So, this value. So, that is what you have an additional peak. So, if you know these type of spectra, you come to know what is the oxidation state of various atoms from the XPS spectra. Now, there are, in the respect to Auger spectra, there are two modes of analyzing this spectra. One is the differential mode, another is the direct mode. In the direct mode, this is the direct mode, what you do is you simply multiply the kinetic energy of the photon which are coming out from the sample into this number. So, if you do that, this is for an XPS spectra of a tungsten foil. So, you have impurities, W is the tungsten here. So, you can see the Auger spectra here like this. You are getting the Auger spectra, but it becomes very difficult to observe this Auger spectra in a direct mode. So, it introduces, so we use a differential mode. What you do, you differentiate with respect to number of electrons, the derivative of the intensity against the kinetic energy. So, these are more distinct. So, what you do is, in the indirect mode, the same spectra will look something like this, like this. So, now you see the Auger peaks are very sharp. So, there are some oxygen and contamination available, nitrogen, carbon, some little bit of phosphorus. So, you see we can also find out the impurities through in a better manner if you do a derivative way. So, it reduces the background and enhance the Auger peaks. In this mode, the Auger energy is depicted with a sharp minimum position with respect to the Auger signal. So, you should always observe the Auger spectroscopy in terms of derivative mode. Now, in this case, the principal Auger KLL peaks of the lighter elements is shown here for sodium, fluorine, oxygen, nitrogen, carbon, boron and beryllium. These are all light elements. Okay. So, for light elements, in these all these light elements, the KLL Auger lines are dominant. All these are KLL Auger lines. When this atomic number goes higher than 15, then MNN or LMM Auger lines then dominates. Okay. So, KLL lines are something like this, that so here I am showing them for lighter elements. Okay. So, lighter elements, all these are KLL lines. So, for example, this is for gold XPS wide scan spectrum. So, if you see, the binding energies are plotted. Now, these are the binding energies. So, binding energies for the valence orbitals. So, these are what? These are valence orbitals. As I told you, it is divided into three valence electrons, 2p, 4f, these are all valence electrons. Then you have the core electrons somewhere here, core electrons. Then here is you have the Auger electrons. Okay. So, for Auger electrons, you see NO, these are pretty high values, because for gold extracting an Auger electron is will require a very high energy. So, you see the Auger electron, these are all direct spectrum. So, in the direct spectrum, you see XPS to be very sharp. So, these initially this you will see NNV, NNN. So, this type of is obtained here 1, 2, 4, 7. In the initial part, you will see the valence electron binding energy 57, 74, 84, like that, it keeps on increasing. So, 4s it is 763, this one is 763. Okay. So, the idea is that to show in this particular spectra both XPS and Auger. So, see, the XPS is very sharp if you observe a direct spectrum, but it is not that sharp when you look up the Auger spectra. So, it is always good to differentiate this with respect to the kinetic energy. And another way, you can also find out what are the elements, particular elements. In this case, you obtain a particular sample from a marine sediment sample. So, what are the elements found? You can find out, see this particular region, the lighter elements, binding energy. So, for aluminum 2p valence. So, you can always observe the valence electrons So, aluminum, silicon, aluminum, all these peaks are available. Along with that, which I have not shown here, you will also get oxygen, carbon, chlorine, silicon, like that. So, this sodium, these are all lower elements can also be detected. So, this is how you use to detect an unknown sample. So, for unknown sample, you compare the binding energy and then you see the reference peaks where the binding energy of what element and what orbital is likely to be. And in the case of Auger electrons, the Auger electrons I have already given the data, it is either KLL, LMM, like that, MNN. So, you observe those energies and try to correlate it with the different elements. And for the transition elements, they usually have a triplet, and this triplet is primarily due to this LMM transition in the case of Auger spectroscopy. In this is the case of iron, you have a triplet at 703, 651, 598. Like that, you have a triplet for magnesium, you have chromium, like that. That is a, you have a fingerprint for the transition elements. So, triplet spectra of transition elements is also very important. Now, if I want to plot these values onto a principal Auger electron charge, so the table there is almost similar, but it is presented when it is actually the LMM KLL. So, the KLL lines you see, these are pretty much dominant when you have till atomic number of 10, while the LMM is dominant when you have a atomic number, let us say 20 to 40. So, here also you can see there will be triplets here, 3 different lines going primarily. So, that is why you see the triplet lines in the previous case for iron. So, for iron you get the triplets for LMM. Then as you go higher and higher molecular weight, you will have the MNN transition to be dominant. So, these are the different atomic element names where you encounter these atomic numbers. So, likewise you have to take this reference peak and apply your where this Auger elements or Auger spectra lie and try to find out the valence. So, the Auger electron spectroscopy, the composition of the several elements. Quantification is it is not accurate, plus minus 10% accurate. So, the total intensity is actually product of the mean atomic concentration of the ith element in the surface under consideration, and sigma I is the cross section of the photoelectron of the ith element, and lambda I is the photoelectron inelastic mean free path for the ith element. K is the factor associated quantitatively for detecting a signal. So, this is more or less a formula used for measuring the intensity. Okay. Now, sometimes the XPS can also measure the thickness of the layer. For example, in the case we want to measure thickness of metallic oxide, for a thin layer less than 9 nanometer, both the metal and metal oxide photoelectrons contribution can be distinguished. For aluminum, the formula is known. So, the thickness layer is equal to 2.8 ln of 1.4 L0 by Lm. The Lm and L0 are the metal and metal oxide peak intensity. So, if you know the peak intensity of this metal oxide, you can find out the thickness. So, this is how it looks like. So, for an aluminum oxide thickness, Al2P spectrum of an aluminum surface is given. The aluminum oxide and metal peaks can assist in the estimation of oxide thickness, which is 3.7 nanometer. So, see, for the pure aluminum it is here. So, as it goes to a different oxidation state, say the binding energy shifts to a higher value, which is because it is attracted more closely, because you extract the electrons, you go to a higher oxidation state. So, you have higher binding energy, same thing has happened. So, this is, so you measure the intensities of these two peaks, put in that expression, that is it, you will get the total thickness, which is 3.7 nanometer. So, this is another application. So, these are in polymers also you get several applications in order to know whether the spectra is totally polymeric or if the particular polymer has degraded. So, if it is degraded, then the energy values will be somewhat different as compared to a pure polymer. So, that also can be used for polymer testing, polymer degradation. So, these are all the uses. So, I will like to say that this XPS spectra and Auger spectra is a very invaluable tool for chemical engineers, especially those who are working or would be working in the field of catalyst. So, where you will come to know what is the amount of element present and in what proportion. So, okay, so you should be able to apply this based on the your particular sample to be characterized. So, I will conclude this module here. You should go through this particular book which defines in detail the various XPS and AES technique. This is given in chapter 7. Then these are the reference books, and you can go to this website where I have taken all the spectra in this particular database, and you can also go through this separately, these books where they have put out all the tabulate the values, the data of Auger spectroscopy and XPS peak in these particular books. Okay, thank you. So, this concludes our module 4, and the next class we will starting our concluding module, which is the module 5, and it will deep on the electrochemical characterization. Thank you.